Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is first detection of dark matter filaments. Using the wide field imaging capabilities of the Subaru telescope, data has been obtained that has led to the first detection of dark matter filaments. 3 observational pieces of evidence suggest that the Big Bang occurred approximately 13.8 billion years ago. The Big Bang marks not just the beginning of space and time, but also the origin of all matter that constitutes our current universe. Initially, matter was concentrated at almost a single point, expanding at an immense speed into a gigantic gas cloud where matter was nearly uniformly distributed. As the universe continued to expand, space became increasingly empty, creating vast voids without matter, while clusters of galaxies gathered in small spaces, forming the large-scale structures of the universe. Observations of the all-sky distribution of 45,000 nearby galaxies, located up to 290 million parsecs away, reveal areas where galaxies are densely clustered, forming galaxy clusters, highlighted in white, and superclusters where these clusters are even more concentrated. Moreover, galaxies and clusters are connected by thin threads resembling a spider's web, referred to as filaments. The large-scale structures of the universe that stand out from these observations only reflect the distribution of baryonic matter visible as galaxies. On the other hand, observations of cosmic microwave background radiation reveal that the composition of the universe at its birth consisted of approximately 68% dark energy, 27% dark matter, and about 5% normal baryonic matter. This indicates that the large-scale structures observed in galaxies represent only a very limited aspect of the universe. Interestingly, the proportion of baryonic matter observed as galaxies is only about 7% of the total baryons, meaning that more than half of the baryons remain undiscovered. This hidden baryonic matter is often referred to as dark baryons or missing baryons. Thus, understanding the growth history of large-scale structures in the universe is key to exploring the nature of dark matter and dark energy. Dark matter collects gas, the raw material for stars, through its gravity, facilitating the formation of galaxies. In contrast, dark energy accelerates the expansion of the universe, hindering structural growth. Therefore, the formation of cosmic structures depends on the balance between these two dark components. The seeds of large-scale structures in the universe are thought to have been created by density fluctuations in matter, observed as temperature fluctuations in cosmic microwave background radiation. In other words, the density fluctuations of dark matter and its properties lead to the formation and evolution of large-scale structures. Dark matter can be broadly categorized into hot dark matter and cold dark matter. Although described as hot and cold, this classification refers not to temperature but rather to the velocity of the particles. Hot dark matter consists of particles, such as massive neutrinos, moving at speeds comparable to the speed of light, while cold dark matter consists of much slower particles. The dominance of either type of dark matter is believed to influence the manner in which cosmic structure forms. If hot dark matter predominates, then fluctuations at smaller scales dissipate due to the high speeds, resulting in the formation of the largest structures, superclusters, first, which then split into galaxy clusters and galaxies. Conversely, if cold dark matter is dominant, small-scale structures form initially, merging and colliding over time to create larger scales of galaxies, galaxy clusters, and superclusters. Consequently, observing the properties and distribution of dark matter could advance our understanding of structure formation. Thus far, the distribution of dark matter has been measured in regions where matter is dense, such as galaxy clusters. In these clusters, the distribution of plasma gas can also be observed alongside galaxies and dark matter. In images like this, the white represents galaxy distribution, pink indicates plasma gas, and blue shows dark matter. It is estimated that galaxies account for about 3% of the mass, plasma gas about 12%, and dark matter around 85%. To understand the universe's large-scale structures, we need to examine the widespread distributions of plasma gas and dark matter. Particularly, the filaments connecting galaxy clusters, as observed in galaxy distributions, remain poorly understood in terms of how they manifest in plasma gas and dark matter. Theoretical predictions suggest that both plasma gas and dark matter weave a similar filamentary structure throughout the universe. Measuring such thinly distributed dark matter requires leveraging weak gravitational lensing effects. Let's quickly revisit gravitational lensing. This phenomenon, explained by Einstein's theory of general relativity, occurs when massive celestial objects like galaxies and galaxy clusters warp spacetime. Light from background celestial objects changes its path as it passes through the distorted spacetime, resulting in gravitational lensing effects. For instance, strong gravitational lensing effects have been observed in galaxy clusters dominated by dark matter, where images of distant galaxies appear arc-shaped due to this effect. True to its name, gravitational lensing only alters the shape and brightness of objects. The strength of this effect depends on the spatial relationships and mass distribution of the lensing object and the background celestial body. The lensing effect can also be produced by dark matter, which is thought to be distributed widely throughout the universe, giving rise to what is known as weak lensing effects. By measuring the weak lensing effects produced by large-scale cosmic structures, referred to as cosmic shear, we can investigate dark matter distribution. When illustrating the universe's large-scale structure, we can represent it schematically. If dark matter also exists along complex filament-like structures, light from distant galaxies in the background would be slightly distorted. By measuring these subtle distortions in individual galaxies, we could determine the distribution of dark matter. However, the original shapes of galaxies can vary, making it difficult to ascertain whether the distortions arise from the lensing effect or are intrinsic. To overcome this challenge, observing many galaxies in the same direction allows for the measurement of systematic distortions. This systematic distortion is known as cosmic shear. This cosmic shear is extremely slight, with the magnitude of shear produced by large-scale structures being only a few %. To measure a value in one direction, it is necessary to observe over 100 galaxies. In summary, to measure the universe comprehensively, extensive observations of numerous galaxies are essential. Utilizing this weak lensing effect, the Subaru telescope's hypersuprime cam, HSC, plays a significant role in measuring dark matter distribution. The Subaru telescope's standout feature is its much wider field of view compared to other 10-meter class ground-based telescopes, the upcoming 30-meter telescope, and the latest James Webb Space Telescope. HSC, which enhances this feature, can capture a sky area of 1.7 square degrees, equivalent to 9 full moons, at once. The sensitivity and imaging performance of HSC are exceptional, garnering worldwide attention for its overwhelming observational capabilities. From HSC observations, the three-dimensional distribution of dark matter is being measured, and a physical quantity known as S8, representing the current state of cosmic structure formation, is being determined. This quantity depends on the amplitude of density fluctuations in mass and the proportion of matter within the total energy. If the standard model of the universe is correct, the values obtained from various observations should align. The value measured by the Subaru telescope was 0.76. This value is consistent with measurements using gravitational lensing conducted with other projects like KEDS and DAY. However, it was found to be smaller than the values derived from measurements of cosmic microwave background radiation by the Planck satellite. Considering the possibility of measurement error alone, there is over a 95% probability of a significant difference. If this difference is significant, it indicates a flaw in current standard cosmology and suggests the potential existence of unknown physics. Thus, further verification is necessary. A research team from Yonsei University in South Korea believes that confirming whether the filament structures found from galaxy distributions also exist in dark matter distributions is crucial for testing standard cosmology. They focused on the Coma cluster, located 321 million light-years from Earth. The Coma cluster is the closest and one of the largest galaxy clusters, making it an optimal target for investigating filament structures formed by dark matter. However, due to its vast apparent spread, high-resolution images with a wide field of view were needed to measure the weak lensing effect. As a result, the research team used publicly available data from the Subaru telescope to measure the dark matter distribution, resulting in the distribution shown here. The background image was captured by HSC, with green indicating the dark matter distribution. The center of the image corresponds to the center of the Coma cluster, home to the giant elliptical galaxy NGC 4874, which is about 10 times the size of the Milky Way. Slightly away from the center lies NGC 4889, which contains the heaviest black hole recorded. Observing individual celestial bodies within the galaxy cluster illustrates the grandeur of the universe, but it also captures the vast dark matter spread radiating from the cluster's center. This is the first time dark matter filaments have been directly confirmed. It is believed that dark matter filaments permeate the universe, and as data analysis from the Subaru telescope progresses along with observations from the Euclid satellite launched in 2023, we can expect a clearer picture of the vast distribution of dark matter in the universe. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.